Hey guys, Professor Floyd here, and we're doing homework 1 and homework 10, problem number 1, and we're talking about mass transport and flow, mostly manipulations of the Bernoulli equation and special examples of the Bernoulli equation. So here we have a, let's see if I can find my problem set. We have water flowing steadily through a 3/4 inch diameter pipe like a garden hose, and then it's moving at 1.6 feet per second, and it passes through a constriction that has a cross-sectional area of 0.11 square inches. So maybe you left your garden hose out, you ran over it with a lawnmower because you let your grass get too tall and didn't see it, and then you decided, oh man, I don't want to throw out this heavy-duty garden hose that I bought, so I'm going to find some pipe. Well, it's 3/4 inch inside diameter. I've got some 3/4 inch iron pipe here, a galvanized pipe. I'll just wedge the hose over top of that, and we're good to go. And so, of course, that galvanized pipe fits inside, and it has wall thickness, and so it makes a constriction. And maybe you remember things from high school chemistry using aspirators, and you're just kind of curious. I wonder if I've made enough of a pressure difference that I can use this setup as an aspirator and create a vacuum. I don't know. You just want to know. I don't know. You're curious. Inquiring minds want to know these things. So you have your garden hose, and then it approaches some sort of constriction, and we don't know equal information here. So we need to take an inventory of what we do know. The first thing we know is that the flow here is constant. So the flow at point 1 is going to be equal as point 2. So Q1 equals Q2. And we know that Q equals velocity times area, because velocity is meters per second and area is square meters, and so that's cubic meters per time, so volume per time, which is flow. Okay, so we know that. So we know that the velocity at point 1 times the area at point 1 has to be equal to the velocity at point 2 times the area at point 2. Now, we can calculate the area from the inside diameter and the fact that it's a circle, it's a tube. We know the velocity, we know the area, so really we're looking for velocity 2. Because eventually, I want you to tell me what's the pressure drop. And to do that, we're going to need delta P is equal to 1/2 density of the fluid times V2 squared minus V1 squared. All right. So we've got to know our velocity at the two different points so that we can figure out what our pressure drop is, because inquiring minds want to know. So V2 is equal to V1 A1 over A2, and now we need to calculate A1. So A1 is equal to pi r squared, and r is half of 0.75. 0.75 divided by 2. Okay. So A1 is equal to, did I calculate that? Yeah. 0.44 squared inches. All right. And then A2 is 0.11, and then V1 is 1.6, and V2 is our unknown. And so we can just calculate that pretty quickly. Because our areas are going to cancel, we don't have to worry about getting them in square feet or anything like that. So just save yourself the unit conversion trouble. And we have 1.6 feet per second multiplied by 0.44 inch squared divided by 0.11 inch squared. So our square inches cancel, and we find out that our V2 is 6.42 feet per second. All right. Now we're ready to just plug into our horizontal flow special case of Bernoulli equation. All right. And so our change in pressure is going to be equal to 1/2 the rho, and then we'll go ahead and calculate what this number is before we start putting any kind of values to these constants. And so our V2 is 6.42 feet per second squared minus our V1, which was 1.6 feet per second squared. Whatever. All right. So I don't really know how you like to do things. I like to just go ahead. I use an old school calculator, so my calculator doesn't do a lot of complex input. And so I just calculate this, calculate that, and then subtract it. So 6.42 squared is 41.22, and then 1.6 squared is 2.56. So the difference between those two is 38.66. All right, and that's in feet squared per seconds squared. That's what's important to note, is what your units are here. So now we can start plugging this in. So our delta, our units in, so that we make sure that we cancel, is 1/2. Our density of water, I like to use SI units, and since we're going to be calculating in PSI, and I just hate messing around with English units when it comes to pressure, unless everything's already in feet and square inches. I would just go ahead and convert over, so I will. It is 1,000 kilograms per cubic meter, and then that is going to be multiplied by our 38.66 feet squared per seconds squared. All right. Now we just got to get rid of our square feet into square meters. And so if you remember, 1 meter is equal to 3.28 feet. I did not remember. I looked it up just a minute ago, and I still remember it. Of course, that only gets rid of one of our feet. So we need to square this and square that. So the beauty of setting it up this way, where the meter is the 1 unit, you only have to do half as much math. It stays the same. Square of 1 is 1. This gets squared, and then your feet square will cancel. So, got a helicopter coming by. And so let's calculate what it is. We have 0.5 times 1,000 times 38.66 divided by 3.28 squared. And so this comes out to 1797. All right. So I know that this comes out to pascals, but I want to prove it to you. And so we have square meters here, and we have cubic meters here. So that just becomes meters. And then we have square seconds. So we have kilograms per meter second squared, and that is a pascal. All right. So we have 1797 pascals, and we need it in PSI because we're in America and we think in PSIs. We generally don't have a great feel for how much pressure a pascal is. So 1797 pascals, and I happen to know that the atmospheric pressure is 101,300 pascals, and that's also 14.7 psi. And we do that. and we find that's 0.26 psi. So not a whole lot of pressure, but there's also, we can know that the sign on this is negative. And so we should know that because as you increase your flow rate, you're converting static pressure into velocity pressure. We could also keep track that the formal way for the horizontal flow is P1 minus P2. Instead of delta P, it's P1 minus P2. And so the fact that we end up with a positive value, I don't know, if you keep track of all your signs, you'll realize that the initial pressure must have dropped in order for the velocity to have increased. So that is the answer to number 1.